The universe has always told us its stories through light, but light only reveals a part of the truth. What if the rest of the story is hidden in the shadows? What if the most important parts are the ones that we can't see? We look into the deep darkness of space. We see the galaxies burning across billions of light years. We see the stars that are being born, the planets that are spinning, and the nebulae glowing with an ethereal light. Yet all of it, everything that we have ever observed, makes up less than 5% of the entire universe. The rest is missing. This is not a theory but a fact, measured, confirmed and real, but completely invisible to our eyes. There is something happening in the very center of our own galaxy. It's a silent, rhythmic signal. A specific and powerful burst of energy is repeating over and over again. It is not coming from a star, and it is not coming from a planet. It comes from annihilation itself. It is the death cry of matter colliding with antimatter. This reaction is so perfect and so complete that it leaves nothing behind but a pure gamma ray. And we are detecting these gamma rays in massive, unimaginable numbers. These are not just accidents, they form vast ghostly clouds, antimatter clouds, floating silently through the galactic core. They are completely invisible to our telescopes and totally undetectable until they destroy something. Physics tells us that they should not exist. The Big Bang should have wiped them out in the first few moments of creation. And yet here they are, waiting. At the same time, something else is lurking in the dark. It wears the face of a black hole, but it is not one. It bends space, it traps light, and it pulls stars into its powerful grip. But inside of it there is not a singularity. It is not a void. It is a shell, a structure, a perfect deception. These are the gravastars, exotic objects thought to arise from quantum gravity forming instead of black holes. They have no event horizon, no infinite collapse, and no information loss. They just have a dense, exotic shell, and inside, nothing but exotic vacuum energy. A perfect, impenetrable mask. From the outside, they are virtually identical to black holes. We could be looking at one right now, and we would never know the difference. There are two cosmic anomalies, one that is real and one that is theoretical. One that destroys silently, and the other that hides in plain sight. They appear to be completely unrelated, separate mysteries floating through space. But maybe they are not. Maybe they are two sides of a much deeper, more profound truth. Maybe what we see is only the cover of a book we were never meant to open. And when we finally understand what they are, we might wish that we never did. This is the hidden universe. The story of our own existence begins with one of the most profound and troubling mysteries in modern physics. According to our current understanding of the universe, you should not exist. Neither should the Earth, the Sun, or any of the billions of galaxies we observe across the cosmos. The very fact that we are here to contemplate our own existence represents a fundamental puzzle. It is a puzzle that has challenged scientists for decades. To understand this cosmic riddle, we must journey back to the very beginning of time itself. We must go to the moment the universe exploded into existence, 13.8 billion years ago, in the event we call the Big Bang. In the first fraction of a second after the Big Bang, the universe was a seething cauldron of pure energy. As temperatures began to drop from the incomprehensible heat of creation, this energy began to condense. It condensed into the first particles of matter. But here is where our story takes a puzzling turn. The fundamental laws of physics tell us that for every particle of matter created, an equal amount of antimatter should have been produced as well. This is not just a theoretical speculation. It is a direct consequence of one of the most important principles in physics, known as charge parity symmetry. When energy converts to matter, it must do so in a way that preserves certain fundamental properties of the universe. For every electron that materializes from pure energy, a positron, its antimatter counterpart should appear alongside it. For every proton, an antiproton. For every neutron, an antineutron. The implications of this symmetry are staggering. If the Big Bang had indeed produced equal amounts of matter and antimatter, the universe would have lasted only a brief moment. It would have destroyed itself completely. Matter and antimatter are perfect opposites. When they encountered each other, they would annihilate instantly, converting back into pure energy with perfect efficiency. No atoms could have formed, no stars could have ignited, and no planets could have coalesced from cosmic dust. Yet here we stand 13.8 billion years later in a universe that is dominated by matter. The stars that light our skies are made of matter. The planets that orbit them are composed of matter. Our bodies, our thoughts, and our very existence are all the products of a universe that chose matter over antimatter. It chose matter for reasons that we do not fully understand. This cosmic preference for matter over antimatter is known as the baryonic asymmetry, and it represents one of the greatest unsolved problems in physics. The calculations suggest that for every billion particles of antimatter produced in the early universe, there were approximately 1,000,000,001 particles of matter. This tiny, almost insignificant imbalance, just one extra matter particle for every billion antimatter particles, is the razor-thin margin that allowed our universe to exist. When the vast majority of matter and antimatter annihilated each other in the universe's first moments, that minuscule excess of matter particles survived. They survived to become everything that we see today. Every atom in your body, every star in the night sky, and every galaxy spanning millions of light years are all the leftover remnants of this cosmic imbalance. But what caused this asymmetry? The Soviet physicist Andrei Sakharov proposed 3 conditions that would need to be met for such an imbalance to occur. First, there must be processes that can change the number of matter particles in the universe. Second, both charge symmetry and charge parity symmetry must be violated under certain conditions. And third, these processes must have occurred when the universe was not in thermal equilibrium. This would be during the rapid expansion and cooling that followed the Big Bang. While physicists have found evidence for some of these conditions, the observed violations are far too small. They cannot account for the massive matter-antimatter asymmetry that we observe. The standard model of particle physics is our best current theory, describing the fundamental forces and particles, but it can only explain a tiny fraction of the imbalance that actually exists. This leaves us with a profound question. What mechanism could have produced such a dramatic preference for matter over antimatter? Various theories have been proposed, from the existence of exotic particles that decay asymmetrically to complex interactions during cosmic inflation. Some scientists have suggested that antimatter might not be as rare as we think. Perhaps it has somehow been segregated into distant regions of the universe where we have not detected it yet. The mystery deepens when we consider that antimatter, though rare, still exists in our universe today. Cosmic ray interactions in our atmosphere produce small amounts of antimatter particles every day. Certain types of radioactive decay create positrons. Even banana peels emit tiny quantities of antimatter as they decompose. More intriguingly, space-based detectors have discovered significant concentrations of antimatter in various regions of our galaxy. These observations suggest that whatever process created the original matter-antimatter asymmetry might still be operating today. It may be continuing to shape the fundamental composition of our universe in ways we are only beginning to understand. Deep within the heart of our galaxy, something extraordinary is happening. Hidden among the billions of stars that make up the Milky Way's central bulge are vast clouds of antimatter. They are silently drifting through space, completely invisible to our telescopes. Yet they announce their presence through the most violent process known to physics: complete annihilation. These antimatter clouds remained completely unknown to science until the late 20th century. That is when our instruments finally became sensitive enough to detect their signature. The story of their discovery begins with a single peculiar energy signature. It puzzled astronomers for decades and ultimately revealed one of the most significant mysteries in modern astrophysics. High-energy gamma-ray detectors began to pick up a strange signal from the direction of the galactic center. Unlike the continuous spectrum of energies typically observed from cosmic sources, this signal appeared at a very specific energy level, 511 keV. This precise energy signature immediately caught the attention of physicists. It corresponds exactly to the energy released when an electron and its antimatter counterpart, a positron, annihilate each other. When matter and antimatter particles collide, they undergo complete annihilation. They convert their entire mass into pure energy. According to Einstein's famous equation, this process produces 2 gamma-ray photons for an electron-positron annihilation. Each one carries exactly 511 keV of energy, the rest mass energy of an electron. The detection of this specific gamma-ray line from space could mean only one thing. Somewhere in the galaxy, electrons and positrons were meeting and destroying each other on a massive scale. The implications of this discovery were staggering. The intensity of the 511 keV line suggested that enormous quantities of antimatter were being annihilated. This was happening near the galactic center every single second. Calculations indicated that the equivalent of several Earth masses worth of antimatter must be destroyed each year. This destruction would produce the observed gamma-ray emission. This represented the largest concentration of antimatter ever detected in the universe. For decades, the 511 keV line remained one of astronomy's most tantalizing mysteries. The limited sensitivity and resolution of early gamma-ray detectors provided only crude measurements. This left scientists to speculate about the true nature and extent of the galactic antimatter phenomenon. It was not until the launch of more sophisticated space-based observatories that the full scope of this cosmic puzzle began to emerge. The European Space Agency's Integral Observatory, launched in 2002, revolutionized our understanding. It changed our understanding of the galactic antimatter distribution. Integral's advanced gamma-ray spectrometer provided unprecedented sensitivity to the 511 keV line. This allowed astronomers to map the antimatter annihilation across the galaxy with remarkable precision. What they discovered defied all expectations. The antimatter signal was not confined to a small region around the galactic center, as many had assumed. Instead, Integral revealed an enormous, roughly spherical cloud of antimatter. It was extending thousands of light-years from the galactic nucleus. This antimatter halo encompassed a significant portion of the galaxy's central bulge. The highest concentrations occurred within about 3,000 light-years of the galactic center. Even more puzzling was the discovery that the antimatter distribution did not follow the same pattern as the visible matter in the galaxy. While stars and gas are concentrated in the galactic disk, the antimatter appeared to be distributed more spherically. This suggested that whatever process was creating these positrons was fundamentally different. It was different from the mechanisms that govern normal stellar activity. The observations from Integral and Fermi painted a picture of truly cosmic proportion. The antimatter annihilation in our galaxy requires the production of around 10 to the power of 43 positrons every single second. This leads us to one of the most perplexing aspects of the galactic antimatter mystery. We can detect antimatter only at the moment of its destruction. The positrons themselves are completely invisible to our instruments until they encounter electrons and annihilate. This produces the telltale 511 keV gamma rays. This means that vast clouds of antimatter could be drifting through space around us. They could be completely undetectable until they interact with ordinary matter. The invisibility of these antimatter clouds presents both a scientific challenge and a potential cosmic hazard. Unlike ordinary matter, which can be detected through various forms of electromagnetic radiation, antimatter particles produce no observable signature. This is true when they are moving through the near vacuum of space. They exist in a state of perfect stealth, revealing themselves only through their ultimate act of self-destruction. Several hypotheses have been proposed to explain the origin of these mysterious antimatter clouds. One leading theory suggests that the positrons are produced by the decay of dark matter particles. Dark matter makes up approximately 85% of all matter in the universe. It remains largely mysterious, but some theoretical models predict that certain types of dark matter particles would decay into electron-positron pairs. The spherical distribution of the antimatter signal matches what would be expected from a dark matter decay. This makes it one of the most compelling explanations. Another possibility involves microquasars, stellar mass black holes, that are actively feeding on material from a companion star. As matter spirals into these black holes, it forms an accretion disk that can reach temperatures of billions of degrees. Under these extreme conditions, intense radiation and magnetic fields could accelerate particles to such high energies. This acceleration could produce electron-positron pairs through various nuclear processes. Pulsars, rapidly rotating neutron stars that emit beams of radiation, represent another potential source of galactic antimatter. The powerful magnetic fields around pulsars can accelerate particles to enormous energies. This could potentially create cascades of secondary particles that include positrons. With thousands of pulsars scattered throughout the galaxy, their collective contribution to the antimatter population could be substantial. More exotic explanations have also been proposed. These include the possibility that primordial black holes left over from the Big Bang might be evaporating. They could be evaporating through Hawking radiation, producing antimatter particles in the process. Some scientists have even suggested that the antimatter clouds might be evidence of an ongoing matter-antimatter asymmetry process. This indicates that the universe is still actively preferring matter over antimatter. It would be doing so through mechanisms that we do not yet understand. The detection of antimatter clouds in our galaxy has opened an entirely new window into cosmic physics. It has revealed processes that operate on scales far beyond anything we can reproduce in terrestrial laboratories. These invisible clouds represent one of the universe's most closely guarded secrets. They announce their presence only through the brilliant flush of their own annihilation. As we continue to study these phenomena, we inch closer to understanding the fundamental forces that shape our cosmic environment. We also get closer to understanding the mysterious processes that continue to create antimatter billions of years after the Big Bang. The mysteries of quantum gravity have long perplexed physicists. They present paradoxes that seem to challenge our fundamental understanding of spacetime itself. At the heart of these puzzles lies the enigmatic nature of black holes and their relationship with quantum mechanics. However, a revolutionary concept has emerged from the depths of theoretical physics. It might hold the key to resolving these cosmic riddles, the gravastars. These exotic objects represent far more than mere alternatives to black holes. They have become crucial testing grounds for our most advanced theories of quantum gravity. They offer insights that could reshape our understanding of reality at its most fundamental level. As we embark on this exploration of gravastars within the framework of quantum gravity theories, we enter a realm. It is a realm where the familiar laws of physics dance on the edge of comprehensibility. Gravastars occupy a unique position in the landscape of quantum gravity research. They serve as theoretical laboratories where the competing forces of general relativity and quantum mechanics meet in a dramatic confrontation. Unlike black holes, which present seemingly insurmountable paradoxes when quantum effects are considered, gravastars offer a framework. It is a framework where these fundamental forces might coexist harmoniously. The significance of gravastars to quantum gravity theorists cannot be overstated. These objects provide a concrete mathematical structure within which to test the predictions of various quantum gravity theories. Where black holes create information paradoxes and infinities that plague our equations, gravastars present finite, well-defined boundaries. These are boundaries that quantum field theory can more readily address. The theory suggests that the extreme curvature within what would be a black hole's interior is prevented by quantum effects. These effects create a repulsive force, effectively halting gravitational collapse before a singularity can form. Loop quantum gravity predicts that when matter reaches a critical density, quantum geometric effects become dominant. This creates what theorists call a quantum bounce. This bounce transforms the would-be black hole into a gravastar. The collapsed matter rebounds outward to form the characteristic vacuum energy shell. The mathematics of this process aligns remarkably well with the gravastar model. This suggests that these objects might be the natural outcome of gravitational collapse in a quantum theory of gravity. String theory, another leading candidate for a theory of quantum gravity, also finds gravastars to be objects of profound interest. In string theory's higher dimensional framework, gravastars represent solutions that avoid the problematic singularities that plague black hole models. The theory's prediction of additional spatial dimensions provides new avenues for understanding. We can understand how the gravastar's internal structure might be supported by quantum effects operating in these extra dimensions. Within string theory, gravastars are often viewed as fuzzballs, extended objects with a finite size rather than point-like singularities. This interpretation suggests that what appears to be a vacuum shell in our familiar three-dimensional space might actually be a complex structure. It may be a structure extended through the theory's additional dimensions. The mathematics of string theory provides natural mechanisms for creating the exotic matter states required to maintain a gravastar structure. This lends theoretical support to their existence. The firewall paradox, one of the most perplexing problems in black hole physics, finds a potential resolution in gravastar models. This paradox arises from the apparent contradiction between the equivalence principle and the requirements of quantum mechanics. The equivalence principle suggests an observer falling into a black hole should experience nothing unusual at the event horizon. Quantum mechanics seems to demand that information cannot be lost. The paradox suggests that a firewall of high-energy particles should exist at the event horizon. This would create a barrier that would incinerate any infalling observer. Gravastars elegantly sidestep this paradox by eliminating the event horizon altogether. Without an event horizon, there is no boundary where quantum effects must create a firewall. Instead, the gravastar's surface provides a physical boundary where information can be preserved. It can be processed according to the standard rules of quantum mechanics. This resolution has attracted considerable attention from theorists who are seeking to understand how gravity and quantum mechanics can be reconciled. The holographic principle suggests that all information contained within a volume of space can be encoded on its boundary. This principle finds a natural application in gravastar physics. The principle arose from black hole thermodynamics. There it was discovered that a black hole's entropy scales with the area of its event horizon, rather than its volume. This scaling suggests that the event horizon somehow encodes all the information that has fallen into the black hole. For gravastars, the holographic principle takes on a new meaning. The gravastar's surface becomes a true physical boundary, where information can be stored and processed. Unlike with black holes, where holographic encoding remains mysterious and paradoxical, gravastars provide a concrete surface. It is a surface where quantum field theory can describe how information is preserved and manipulated. This makes gravastars particularly attractive to theorists working on the holographic description of gravity. The mathematical framework of gravastar physics provides explicit mechanisms for information processing. These are mechanisms that are absent in black hole models. Quantum field theory on the gravastar's surface can describe how information is encoded, stored, and eventually released. This provides a complete picture of the object's thermodynamic evolution. This completeness makes gravastars particularly valuable for testing our understanding of quantum gravity. Recent advances in quantum gravity theory have further strengthened the case for gravastars. Developments in the anti-de Sitter conformal field theory correspondence have shown that gravastar-like objects naturally emerge. This correspondence is a powerful tool for studying quantum gravity, and these objects emerge from quantum field theory calculations. These results suggest that gravastars are not mere mathematical curiosities. They might represent the true fate of matter undergoing gravitational collapse in a quantum theory of gravity. The study of gravastars has also revealed deep connections between quantum gravity and condensed matter physics. The exotic matter states required to maintain a gravastar structure are analogous to quantum condensates studied in laboratory settings. These connections have led to new insights into the nature of space-time itself. They suggest that the fabric of the universe might have more in common with condensed matter systems than was previously imagined. Beyond the familiar tapestry of stars and galaxies that illuminate our night sky lies a vast hidden universe. It is populated by objects so elusive that they challenge our very conception of cosmic reality. These invisible entities drift through the cosmic void. Their presence is felt only through the subtlest gravitational whispers and the most sensitive instruments of modern astronomy. As we venture deeper into this shadowy realm, we discover that the universe's most profound secrets are often concealed in plain sight. They are waiting to be unveiled by those bold enough to look beyond the visible spectrum. The cosmos harbors countless mysteries that reveal themselves only to the most persistent observers. While telescopes capture the brilliant light of distant stars and the swirling arms of spiral galaxies, they miss entirely the dark territories. These are the places where stranger objects dwell. These hidden entities outnumber their luminous counterparts by staggering margins. They form a parallel universe of invisible matter and energy that shapes the very structure of space and time itself. Among the most enigmatic of these hidden entities are the dark galaxies. These are ghostly structures that contain almost no stars, yet possess the gravitational mass of entire galactic systems. These phantom galaxies drift through the cosmic web like invisible leviathans. Their presence is detectable only through their gravitational influence on nearby luminous matter. Composed almost entirely of dark matter and hydrogen gas, they represent failed attempts at galaxy formation. They are cosmic nurseries where the spark of star formation never quite ignited. The discovery of dark galaxies has revolutionized our understanding of cosmic evolution. These objects suggest that the universe contains far more structure than was previously imagined. It has vast networks of dark matter halos supporting invisible galaxies. These galaxies never developed the stellar populations that we associate with normal galactic formation. Some astronomers estimate that dark galaxies may outnumber visible galaxies by factors of 10 or more. This creates a hidden cosmic infrastructure that influences the motion and evolution of every luminous object we observe. Within these dark galaxies, hydrogen gas swirls in complex patterns. It occasionally betrays their presence through radio emissions that are detectable by specialized telescopes. The gas moves according to the gravitational dictates of unseen dark matter. This creates velocity patterns that map the invisible scaffolding of these ghostly structures. Some dark galaxies show evidence of attempted star formation. Small pockets of gas show signs of collapse and heating, only to be quenched by mechanisms that remain poorly understood. Wandering through the vast emptiness between galaxies, another class of invisible objects pursues solitary journeys. They travel across cosmic distances. These are the rogue black holes ejected from their parent galaxies through gravitational interactions or galactic merges. They travel at tremendous speeds through intergalactic space. Their presence is revealed only when they occasionally encounter and consume stray matter. This creates brief flashes of X-ray emission that quickly fade back into darkness. The existence of rogue black holes was first suspected when astronomers noticed unexplained gravitational lensing effects. These effects were in otherwise empty regions of space. These wandering monsters, some containing the mass of millions of suns, bend light from distant galaxies. They bend light as they pass between us and the more distant objects. Their trajectories tell stories of violent galactic encounters. They tell of cosmic billiard ball collisions that occurred billions of years ago. These collisions continue to influence the distribution of matter throughout the universe. Some rogue black holes travel in pairs, binary systems that were ejected together from their parent galaxies. These cosmic fugitives spiral around each other as they journey through the intergalactic medium. They slowly lose energy through gravitational wave emission. Eventually, they will merge in spectacular collisions that send ripples through space-time itself. These are events that can be detected by gravitational wave observatories even when the black holes themselves remain invisible. The theoretical zoo of invisible objects extends far beyond dark galaxies and rogue black holes. It extends into realms where exotic physics creates entities that challenge our understanding of matter itself. Among these are the hypothetical neutrino stars. These are objects so dense that even neutrinos, the most weakly interacting particles in the Standard Model, become trapped within their gravitational embrace. These objects would be virtually undetectable through any conventional means. They would interact with ordinary matter only through the weakest of forces. Neutrino stars represent a theoretical extreme where the universe's most abundant particles become concentrated. These particles normally pass through entire planets without interaction, but they become so concentrated that they form gravitationally bound objects. The conditions required for neutrino star formation push the boundaries of known physics. They require densities that exceed even those found in neutron stars. If they exist, these objects would be among the most exotic structures in the universe. They would be composed entirely of particles that barely acknowledge the existence of ordinary matter. Even more exotic are cueballs, theoretical objects predicted by certain extensions of the Standard Model of particle physics. These are non-topological solitons, stable lumps of scalar field energy. They maintain their structure through quantum mechanical effects rather than gravitational binding. Cueballs could range in size from microscopic particles to objects with planetary masses. All of them would be held together by the self-interaction of exotic scalar fields. The search for cueballs has driven astronomers to look for unexplained gravitational effects. They look in regions of space where no visible matter exists. These objects would be completely dark, emitting no electromagnetic radiation. However, they would still exert a gravitational influence on their surroundings. Some theories suggest that cueballs could be components of dark matter. Dark matter is made of invisible particles that make up the majority of the universe's mass but interact only through gravity. Axion condensates represent another category of invisible objects that could populate the hidden universe. These theoretical structures arise from the Bose-Einstein condensation of axions. Axions are hypothetical particles proposed to solve certain problems in quantum chromodynamics. Axion condensates would form when large numbers of these particles cooled to temperatures near absolute zero. This would create macroscopic quantum objects with properties unlike anything in ordinary matter. The formation of axion condensates could occur in the early universe or in the cold depths of intergalactic space. This is where temperatures approach the cosmic microwave background radiation. These objects would be essentially invisible to electromagnetic observation, but they could be detected through their gravitational effects or their influence on the propagation of electromagnetic radiation through space. Some theoretical models suggest that axion condensates could form cosmic strings or domain walls. These are extended structures that stretch across vast distances through the universe. These objects would be thinner than atomic nuclei, but could extend for millions of light years. They would create invisible barriers that influence the motion of galaxies and the distribution of matter on cosmic scales. The study of these invisible objects has profound implications for our understanding of cosmology and fundamental physics. They suggest that the universe contains far more structure and complexity than visible observations reveal. There are entire categories of objects existing in a shadow realm beyond the reach of conventional telescopes. The gravitational effects of these invisible entities shape the evolution of visible matter. They create the cosmic web of galaxies and galaxy clusters that we observe today. Recent advances in observational techniques have begun to reveal the signatures of these hidden objects. They are revealed through their subtle influences on the visible universe. Gravitational lensing surveys map the distribution of dark matter. This reveals the invisible scaffolding that supports the visible galaxies. Gravitational wave detectors capture the collisions of invisible black holes. This provides direct evidence of objects that emit no light but create ripples in space-time itself. The search for invisible objects has also driven the development of new theoretical frameworks. These frameworks challenge our understanding of the fundamental nature of reality. These theories suggest that visibility and existence are not synonymous. They suggest the universe contains vast realms of matter and energy that interact only weakly with the familiar particles and forces of everyday experience. As we continue to explore this invisible cosmos, we are reminded that our perception of the universe is limited. It is limited by the narrow window of electromagnetic radiation that our instruments can detect. Deep within the cosmic void, separated by vast expanses of nearly empty space, could there exist entire galaxies? Could these galaxies be composed entirely of antimatter? This possibility, once relegated to the realm of science fiction, has emerged as a serious theoretical consideration. It is a consideration among cosmologists who are grappling with the fundamental asymmetries of our universe. These hypothetical antimatter galaxies would shine with the same brilliant light as their matter counterparts. Their anti-stars would be burning anti-hydrogen and anti-helium in nuclear furnaces that mirror our own sun. Yet they would remain invisible to us as antimatter structures. They would betray their exotic nature only through the most subtle observational signatures. The theoretical foundation for antimatter galaxies rests on one of the most perplexing mysteries in cosmology. That mystery is the apparent absence of antimatter in the observable universe. According to our current understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter. Yet today we observe a universe that is dominated almost entirely by ordinary matter. This asymmetry, known as the baryon asymmetry problem, suggests one of two things. Either some unknown process destroyed most of the antimatter in the early universe, or that antimatter was somehow segregated into regions beyond our current observational reach. The segregation scenario opens the tantalizing possibility that antimatter galaxies could exist in isolation. They would be separated from matter-dominated regions by vast distances that prevent catastrophic annihilation events. In this model, the early universe underwent a process of matter-antimatter separation. Different regions evolved along divergent paths. While our local cosmic neighborhood became dominated by matter-distant, regions might have developed into antimatter territories. These territories would be complete with antimatter galaxies, antimatter stars, and perhaps even antimatter planets. An antimatter galaxy would appear remarkably similar to a normal galaxy when observed from afar. Antiprotons and positrons would form antihydrogen atoms. These atoms would emit photons identical to those produced by ordinary hydrogen. Antistars would shine with the same spectrum as normal stars. Their surface temperatures would be determined by the same nuclear physics that governs stellar evolution in our matter-dominated universe. The gravitational forces that shape galactic structure would operate identically on antimatter. This would create spiral arms, galactic bars, and central bulges that mirror the morphology of familiar galaxies. However, the boundaries between matter and antimatter regions would be marked by spectacular annihilation events. Where the tenuous gas of intergalactic space meets its antimatter counterparts, a mutual annihilation would produce intense gamma-ray emission. This would create bright annihilation edges that could serve as observational signatures of antimatter galaxies. These boundary regions would glow with the characteristic gamma-ray energies of 511 kilo-electron-volts. This is the signature of electron-positron annihilation. They would also glow with higher energy gamma rays from proton-antiproton interaction. The search for antimatter galaxies has driven astronomers to examine cosmic ray data with unprecedented precision. They are looking for the telltale signatures of antihelium nuclei. Cosmic rays, the high-energy particles that pervade the galaxy, consist primarily of protons and helium nuclei. They were accelerated to tremendous energies by supernova explosions and other violent astrophysical events. In our matter-dominated galaxy, antihelium nuclei are virtually non-existent. They are produced only in trace amounts by high-energy particle collisions. The detection of antihelium in cosmic rays would provide compelling evidence for antimatter galaxies. While single antiprotons can be produced through conventional particle interactions, the creation of antihelium nuclei requires extremely rare conditions. These conditions are rare in our matter-dominated universe. The presence of antihelium would suggest that somewhere in the cosmos antimatter stars are burning antihydrogen. They would be ejecting antihelium through stellar winds and supernova explosions. This is much as ordinary stars produce and distribute the heavier elements we observe in cosmic rays. Recent experiments aboard the International Space Station have pushed the sensitivity of antihelium detection to unprecedented levels. The Alpha Magnetic Spectrometer, a sophisticated particle detector, has analyzed millions of cosmic ray events. It has been searching for the rare signature of antihelium nuclei. While no definitive detection has been made, the experiments have established upper limits. These limits on the abundance of antihelium constrain the possible existence of nearby antimatter galaxies. Theoretical models for antimatter galaxy formation suggest that these objects would produce their own antimatter clouds. They would do this through processes analogous to those that create the interstellar medium in ordinary galaxies. Antimatter stars would end their lives in antimatter supernovae. They would eject processed antimatter elements into the surrounding space. These antimatter clouds would serve as the raw material for subsequent generations of antimatter stars. This would create a self-sustaining cycle of antimatter stellar evolution. The antimatter clouds surrounding these galaxies would be detectable through their interaction with the cosmic microwave background radiation. The anti-electrons in these clouds would scatter photons from the cosmic microwave background. This would create distortions that could be measured by sensitive microwave telescopes. The Sunyaev-Zeldovich effect, which is normally used to detect hot gas in galaxy clusters, could also reveal the presence of antimatter clouds. This is possible if they exist in sufficient quantities. The observational constraints on antimatter galaxies come from several independent sources. Gamma-ray telescopes have surveyed the entire sky. They have been searching for the intense gamma-ray emission that would mark the boundaries between matter and antimatter regions. The absence of such signals places strict limits on how close antimatter galaxies could be to our own cosmic neighborhood. Current observations suggest that if antimatter galaxies exist, they must be separated from matter-dominated regions. The separation must be by distances of at least several 100 million light-years. The cosmic microwave background radiation provides another constraint on antimatter galaxies. The remarkable uniformity of this primordial radiation suggests that matter and antimatter were mixed on large scales in the early universe. This makes it difficult to explain how they could have separated into distinct regions without leaving detectable signatures. These signatures would have been left in the cosmic microwave background. Sophisticated computer simulations of the early universe have shown something interesting. The required level of matter-antimatter segregation would likely produce temperature fluctuations in the cosmic microwave background. These fluctuations would exceed those that were actually observed. Despite these constraints, some theoretical models continue to allow for the existence of antimatter galaxies. These would exist in the distant universe. These models invoke exotic physics from the very early universe. They suggest that quantum fluctuations or phase transitions could have created domains of matter and antimatter that evolved separately. In these scenarios, antimatter galaxies would exist in regions so distant that their annihilation signatures would be redshifted. They would be redshifted beyond the detection capabilities of current instruments. The search for antimatter galaxies has also motivated the development of new theoretical frameworks. These frameworks help us understand cosmic evolution. Some models propose that antimatter galaxies could exist in parallel branes or extra dimensions. They would interact with our universe only through gravity. These scenarios would explain why antimatter galaxies remain invisible to electromagnetic observation. They would still be contributing to the total gravitational mass of the universe. Advanced computer simulations have been developed to predict the observational signatures of antimatter galaxies. These predictions fall under various theoretical scenarios. These models account for the complex interactions between matter and antimatter in the intergalactic medium. They also account for the propagation of gamma rays through cosmic distances and the effects of cosmic expansion on annihilation signals. The results provide detailed predictions for what current and future telescopes should observe if antimatter galaxies exist. The implications of discovering antimatter galaxies would be profound. They would be profound for our understanding of fundamental physics and cosmology. Such a discovery would require a complete revision of our models for the early universe. It would suggest that processes beyond the standard model of particle physics played a crucial role in cosmic evolution. It would also raise fascinating questions about the possibility of antimatter life. And it would raise questions about the potential for antimatter civilizations developing in isolation from our matter-dominated region of the universe. Future observational missions may finally resolve the question of antimatter galaxies. The next generation gamma-ray telescopes with unprecedented sensitivity will search for faint annihilation signals. These signals would mark the boundaries of antimatter regions. In the vast theater of cosmic phenomena, two of the most enigmatic entities present themselves. They are mirror reflections of the fundamental mysteries that challenge our understanding of reality itself. Gravastars represent hidden structures that masquerade as familiar objects. They conceal exotic physics within their deceptive shells. Antimatter galaxies embody the missing substances that should exist in abundance, yet they remain tantalizingly absent from our observable universe. These two phenomena, though seemingly unrelated, share profound connections. These connections illuminate the deepest questions about the nature of space-time and the hidden mechanisms that govern cosmic evolution. The parallel between gravastars and antimatter extends far beyond their mutual invisibility. Both represent fundamental challenges to our assumptions about the fabric of space-time. They also challenge the processes that shape cosmic structure. Where gravastars question the inevitability of singularities and the nature of gravitational collapse, antimatter galaxies challenge our understanding. They challenge our understanding of cosmic symmetry and the mechanisms that led to the matter-dominated universe we observe. The hidden structure of gravastars presents a cosmic sleight of hand. Objects that appear to be black holes actually conceal radically different physics beneath their surfaces. This deception operates on multiple levels. It operates from the macroscopic appearance of the object to the microscopic quantum processes that maintain its structure. Similarly, antimatter galaxies represent a cosmic hide-and-seek game. Entire galactic structures could exist in plain sight. Their true nature would be concealed by the identical electromagnetic signatures they share with ordinary matter galaxies. Both gravastars and antimatter galaxies emerge from the same fundamental tension between theory and observation. This is the tension that drives modern physics. Gravastars arise from the incompatibility between general relativity and quantum mechanics. They represent an attempt to resolve the paradoxes that plagued our understanding of extreme gravitational environments. Antimatter galaxies emerge from the disconnect between the symmetric laws of particle physics and the asymmetric universe we observe. This suggests vast regions of space might harbor the missing antimatter that theories predict but observations fail to detect. The theoretical frameworks that support these phenomena share remarkable structural similarities. Both require exotic physics that operates beyond the boundaries of our current observational capabilities. Gravastars demand exotic matter with a negative pressure and unusual equation of state properties. These properties have never been directly observed. Antimatter galaxies require segregation mechanisms that operated in the early universe. These mechanisms would create regions of space where antimatter could evolve in isolation from ordinary matter. These requirements push both phenomena into the realm of speculative physics. This is where theoretical elegance must substitute for empirical verification. The observational challenges posed by gravastars and antimatter galaxies mirror each other in striking ways. Both phenomena would appear nearly identical to conventional objects when viewed through electromagnetic radiation. They would require subtle gravitational or high-energy signatures to reveal their true nature. The detection of gravastars relies on minute differences in gravitational wave signatures. It also relies on tidal effects and the behavior of matter in extreme gravitational fields. The identification of antimatter galaxies depends on detecting annihilation radiation. It also depends on anti-helium in cosmic rays and subtle distortions they would create in the cosmic microwave background. The concept of symmetry breaking plays a crucial role in both phenomena. Gravastars represent a breaking of the expected symmetry between gravitational collapse and black hole formation. They introduce quantum effects that prevent the formation of classical event horizons. Antimatter galaxies embody the ultimate expression of a broken matter-antimatter symmetry. They suggest the universe's fundamental asymmetry might be more complex than was previously imagined. There could be regions of space evolving along entirely different evolutionary paths. The possibility that gravastars could form in regions dominated by antimatter opens fascinating avenues. This is a fascinating path for theoretical exploration, Antimatter would undergo gravitational collapse in precisely the same manner as ordinary matter. This would create the conditions where gravastar formation becomes possible. An antimatter gravastar would possess all the exotic properties of its matter counterpart. It would have an antiparticle vacuum shell preventing the formation of a classical event horizon. These objects would be doubly invisible. They would be concealing both their gravastar nature and their antimatter composition beneath a facade of apparent normality. The formation of antimatter gravastars would require the same exotic physics that supports ordinary gravastar formation, but it would have the added complexity of antimatter evolution in isolated cosmic environments. The quantum field theory that describes vacuum fluctuations and exotic matter states would operate identically in antimatter regions. This would create the same conditions necessary for gravastar formation. However, the boundary between matter and antimatter regions would introduce additional complications. The annihilation of matter and antimatter at these interfaces could influence the formation and stability of gravastars in the boundary regions. The observational signatures of antimatter gravastars would be even more subtle than those of their ordinary matter counterparts. The gravitational waves produced by an antimatter gravastar formation would be indistinguishable from those produced by ordinary matter systems. This is because gravity couples identically to matter and antimatter. The detection of such objects would require identifying both gravastar signatures and antimatter indicators. This is a double challenge that pushes observational capabilities to their absolute limits. Both phenomena raise profound questions about the nature of information and its preservation. They raise questions about its preservation in extreme physical environments. Gravastars offer potential solutions to the black hole information paradox. They do this by eliminating the event horizon that threatens to destroy information. Antimatter galaxies preserve information in a different way. They maintain the symmetric information content of the universe by segregating rather than destroying antimatter. These different approaches to information preservation suggest that the universe may employ multiple strategies. It may employ strategies for maintaining the fundamental conservation laws that govern physical processes. The thermodynamic properties of gravastars and antimatter galaxies reveal additional connections between these phenomena. Both systems exist in states of a delicate equilibrium. This equilibrium is maintained by the balance between competing forces that operate on vastly different scales. Gravastars balance quantum pressure against gravitational collapse. Meanwhile, antimatter galaxies balance annihilation, destruction against segregation preservation. These equilibrium states suggest that the universe naturally evolves toward configurations that maximize the preservation of information and structure. The role of vacuum fluctuations connects gravastars and antimatter galaxies through the quantum nature of space-time itself. The vacuum energy that supports gravastar shells arises from the same quantum field fluctuations that could have driven matter-antimatter segregation. This would have happened in the early universe. These fluctuations represent the fundamental graininess of space-time at the Planck scale. This is where the classical concepts of matter and geometry break down and give way to purely quantum descriptions of reality. The mathematical frameworks used to describe gravastars and antimatter galaxies share deep structural similarities. These similarities are rooted in field theory and general relativity. Both phenomena require extensions of standard physics that invoke exotic matter. They also invoke unusual vacuum states and non-trivial topology. The equations that govern gravastar dynamics and antimatter evolution emerge from the same underlying principles. These are the principles of quantum field theory in a curved spacetime. This suggests that these apparently disparate phenomena may be manifestations of the same deeper physical principles. The experimental and observational programs designed to detect gravastars and antimatter galaxies employ complementary strategies. Together they probe the full range of cosmic phenomena. Gravitational wave detectors, cosmic ray experiments, gamma-ray telescopes, and precision measurements of stellar dynamics all contribute. They all contribute to the search for these elusive objects. The synergy between these different approaches suggests that the discovery of either phenomenon would likely accelerate progress in detecting the other. The philosophical implications of gravastars and antimatter galaxies extend beyond their immediate physical significance. They extend to questions about the nature of scientific knowledge and the limits of observation. Both phenomena force us to consider the possibility that the universe contains vast realms of hidden structure and missing substances. These realms lie beyond our current observational reach. They remind us that the electromagnetic radiation that forms the basis of traditional astronomy provides only a narrow window into cosmic reality. And they remind us that the most profound discoveries may await in the invisible territories that lie beyond the reach of conventional telescopes. In the vast catalogue of cosmic objects that populate our universe, few capture the imagination quite like black holes. These gravitational monsters born from the collapse of massive stars have become icons of modern astronomy. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This is true once it crosses the point of no return known as the event horizon. But what if everything we think we know about black holes is fundamentally wrong? This revolutionary possibility emerged in 2001. Two physicists, Paul Mazur and Emil Mottola, proposed one of the most radical ideas in modern astrophysics. Mazur was from the University of South Carolina, and Mottola was from the Los Alamos National Laboratory. Their theory suggested that the objects we identify as black holes might actually be something entirely different. They could be exotic structures that they called gravastars, which is short for gravitational vacuum stars. The gravastar hypothesis challenges our most basic assumptions about what happens when matter undergoes gravitational collapse. According to conventional theory, a star more than about 25 times the mass of our Sun exhausts its nuclear fuel. Then the outward pressure from fusion reactions can no longer support the star against its own gravity. The star's core collapses, catastrophically crushing matter to an infinite density at a point called a singularity. Meanwhile, the surrounding space-time becomes so warped that it forms an event horizon, a boundary beyond which nothing can return. Mazur and Mottola proposed a radically different scenario. Instead of collapsing all the way to a singularity, they suggested that the star's interior might undergo a phase transition. This is a fundamental change in the state of matter itself. At the moment when gravitational pressure becomes overwhelming, the fabric of space-time itself might respond. It might respond by entering an exotic state known as a de Sitter vacuum. This de Sitter vacuum represents one of the most mysterious concepts in modern physics. It was named after the Dutch mathematician Willem de Sitter. It describes a state of space-time that contains no matter or radiation, yet possesses a strange property. It exerts a negative pressure, effectively pushing outward rather than inward. This negative pressure creates a repulsive gravitational effect. This effect could halt the collapse of matter before a singularity forms. The internal structure of a gravastar, as envisioned by Mazur and Mottola, would be unlike anything in our normal experience. At its core would be a sphere of de Sitter vacuum, an empty space that paradoxically possesses energy and exerts pressure. This quantum vacuum core would be surrounded by an incredibly thin shell of exotic matter. This shell would perhaps be only a few Planck lengths thick. This shell would be composed of matter in a state we have never observed directly. It would exist at the boundary between normal space-time and the strange de Sitter interior. From the outside, a gravastar would appear to be virtually identical to a black hole. It would possess the same mass, the same gravitational field, and the same effect on nearby objects. A spacecraft orbiting a gravastar would follow the same trajectories as those orbiting a black hole. Light passing near a gravastar would be bent by gravity in exactly the same way. Even the powerful gravitational waves produced when two gravastars collide would be nearly indistinguishable. They would be almost the same as those created by merging black holes. This remarkable similarity makes gravastars nearly perfect imposters. The gravitational field outside any spherically symmetric object depends only on its total mass and distance. This is regardless of how that mass is distributed internally. This principle, known as Birkhoff's theorem, means that we cannot easily distinguish between a black hole and a gravastar. We cannot do this using observations from outside the object. However, the internal differences between black holes and gravastars are profound. While a black hole contains a singularity, a point where the laws of physics break down completely, a gravastar would have no such pathological region. Instead of an infinite density concentrated at a point, the gravastar's mass would be distributed in its exotic matter shell. The interior would remain an empty de Sitter space. The absence of a singularity resolves several troubling paradoxes that have plagued black hole physics for decades. In traditional black hole theory, the singularity represents a fundamental breakdown of our understanding of physics. At this point, density becomes infinite, space-time curvature becomes infinite, and the equations of general relativity cease to provide meaningful predictions. The gravastar model eliminates this problem entirely by preventing the formation of a singularity in the first place. Perhaps even more significantly, gravastars would not possess event horizons. The event horizon of a black hole represents a point of no return. It is a boundary that forever separates the interior from the external universe. Once something crosses the event horizon, it can never communicate with the outside world again. This leads to profound questions about the nature of information and causality in our universe. The absence of an event horizon in gravastars eliminates several paradoxes that have puzzled physicists for generations. One of the most famous is the black hole information paradox. This arises from the conflict between general relativity and quantum mechanics. According to quantum mechanics, information cannot be destroyed. It can only be transformed or hidden. But if matter falls into a black hole and disappears forever behind the event horizon, then what happens to the information it carried? Stephen Hawking's discovery that black holes can evaporate through quantum radiation only deepened this paradox. If a black hole eventually evaporates, completely carrying away the information that fell into it, this would violate a fundamental principle. It would violate one of the fundamental principles of quantum mechanics. The information paradox has led to decades of theoretical work. It continues to challenge our understanding of the relationship between gravity and quantum mechanics. Gravastars offer an elegant solution to this dilemma. Without an event horizon, information falling toward a gravastar would never be permanently lost. Instead, it would be stored in the exotic matter shell. It would potentially be recoverable through future observations or interactions. This preservation of information would maintain the consistency of quantum mechanics. It would do this while still explaining the gravitational effects that we observe. The quantum vacuum at the heart of a gravastar represents another departure from conventional black hole physics. Instead of the empty nothingness that classical physics would predict, quantum field theory tells us something different. It tells us that even empty space is filled with virtual particles. These are pairs of particles and antiparticles that spontaneously appear and disappear on timescales too short to observe directly. In the extreme conditions near a black hole, these virtual particles can be separated. One falls into the black hole while the other escapes as Hawking radiation. In a gravastar, the de Sitter vacuum core would be in a fundamentally different state. Rather than the quantum vacuum we observe in normal space, it would exist in a configuration with a negative pressure. This is a state that could theoretically persist indefinitely without the gradual evaporation that affects black holes. This stability would allow gravastars to exist for timescales far longer than the current age of the universe. They could potentially outlast even the protons that make up ordinary matter. The formation mechanism for gravastars remains one of the most challenging aspects of the theory. Unlike black holes, which form through the relatively straightforward process of gravitational collapse, gravastars would require something else. They would require the creation of exotic matter and the establishment of a de Sitter vacuum core. The exact physical processes that could accomplish this transformation remain speculative. They involve aspects of quantum gravity and exotic matter physics that we do not yet fully understand. Some theoretical work has suggested that gravastars might form during the final stages of stellar collapse. This is when quantum effects become important. As matter approaches the point where a singularity would form, the quantum corrections to general relativity might become significant. They could be significant enough to prevent further collapse. The resulting phase transition could create the exotic matter shell and the de Sitter core that characterize a gravastar. The search for observational evidence of gravastars has become one of the most intriguing challenges in modern astronomy. Since gravastars would appear nearly identical to black holes from the outside, distinguishing between them requires extremely subtle observations. Some researchers have proposed looking for slight differences in gravitational wave signatures. They have also proposed looking for variations in the behavior of matter spiraling into these objects. Or they could look for other minute deviations from black hole predictions. Recent advances in gravitational wave astronomy have opened new possibilities for testing the gravastar hypothesis. The collision of two gravastars would produce gravitational waves with characteristics that might differ slightly. They would differ from those of merging black holes. As our detectors become more sensitive and our theoretical understanding improves, we may finally be able to determine something. We could determine whether the cosmic objects we call black holes are truly the gravitational monsters we imagine, or perhaps they are something far stranger, bubbles of exotic space-time masquerading as the universe's most extreme objects. From the outside, a gravastar appears to be an exact twin of a black hole. The space-time around both objects bends and warps in precisely the same way. This creates what scientists call identical external metrics. To any distant observer, their gravitational fields look indistinguishable. The same crushing pull bends light and time itself. The same fierce gravitational embrace captures passing matter and accelerates it to incredible speeds. It heats the matter until it glows with the fury of 1,000 suns. But hidden within this cosmic masquerade lies a profound mystery. While black holes and gravastars may look identical from afar, they harbor fundamentally different secrets in their cores. The question that keeps astrophysicists awake at night is simple yet profound. How can we tell them apart? How do we distinguish between nature's most extreme objects when they wear identical masks? The challenge is immense. A gravastar's surface sits precisely where a black hole's event horizon would be. This is the critical radius where escape velocity equals the speed of light. Yet despite this perfect camouflage, the universe may still whisper their secrets to those who know how to listen. The answer lies in the most subtle signals that nature produces: gravitational waves. When two massive objects spiral toward each other in their final cosmic dance, they send ripples through space-time itself. These waves carry the very fingerprints of their source. They are encoded in the frequencies and amplitudes that tell the story of their violent origins. The gravitational waves from gravastars are remarkably similar to those of black holes, but the tones and the fadings are different. Like two master violinists playing the same complex piece, A trained ear can detect the subtle differences in timbre and resonance. Scientists have discovered that gravastars should produce slightly different gravitational wave patterns. These are variations so minute that they exist at the very edge of our current detection capabilities. The difference lies in what happens during the final moments of a collision. When two black holes merge, they create a characteristic pattern, an initial in-spiral as the objects circle each other, followed by a brief but intense merger phase, and finally a ring-down as the newly formed black hole settles into its final state. This ring-down phase carries the signature of the event horizon, that invisible boundary where information disappears forever. Gravastars, however, possess actual surfaces. During a collision, these surfaces can vibrate and oscillate in ways that event horizons cannot. The result should be additional gravitational wave signatures. These are subtle echoes that reverberate through space-time like a sound bouncing off the walls of a vast cathedral. These echoes would arrive milliseconds after the main signal. They would be carrying information about the structure and composition of the colliding objects. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has been listening to these cosmic symphonies since 2015. Each detection tells a story of cataclysmic collisions from billions of years ago. These were events so violent that they briefly outshone entire galaxies in gravitational wave energy. But hidden within these signals could be evidence of something far more exotic than black holes. When LIGO detects a gravitational wave event, teams of scientists pore over the data with microscopic attention to detail. They search for anomalies, for patterns that do not quite match the theoretical predictions for black hole merges. In the case of gravastars, they hunt for what they call echo signals. These are the subtle reverberations that might occur if the colliding objects have surfaces rather than event horizons. The search is painstaking and requires extraordinary precision. The gravitational waves that reach Earth are incredibly weak. They stretch and compress space by distances that are smaller than 1,000th of a proton's width. Detecting echoes within these signals is like trying to hear a whisper in a hurricane. It requires signal processing techniques that push the boundaries of modern technology. So far, the echoes remain elusive. The dozens of gravitational wave events detected by LIGO and its European counterpart Virgo are all consistent with black hole merges. Yet they cannot definitively rule out gravastars. The cosmic truth remains tantalizingly out of reach. It is hidden in the noise and uncertainty that plague the most sensitive measurements ever attempted. Perhaps the most direct way to distinguish between these cosmic twins lies not in the waves they produce. Perhaps it lies in the light that they bend. The Event Horizon Telescope has given us our first glimpse of what we believe to be a black hole's shadow. It is the iconic image of M87, a dark silhouette against the glowing accretion disk surrounding it. This groundbreaking photograph shows us the very edge of the point of no return. This is where light itself cannot escape. The image reveals a ring of fire surrounding a dark void, exactly as Einstein's equations predicted more than a century ago. The shadow that we see is not the black hole itself. Rather, it is the absence of light from the region within the event horizon. It represents the ultimate boundary of the observable universe. It is the place where physics, as we understand it, breaks down completely. But what if that shadow belongs to something else entirely? What if M87 is actually a gravastar masquerading as a black hole? The current telescope technology cannot distinguish between a black hole and a gravastar based on their shadows alone. The Event Horizon Telescope, despite its remarkable achievement, operates at the very limits of what is physically possible. Creating a more detailed image would require a telescope the size of Earth's orbit. This is a feat that remains firmly in the realm of science fiction. We stand at the threshold of a new era in astronomy. The tools we have built to study the universe are revealing mysteries that challenge our fundamental understanding of reality. The question of whether gravastars exist may ultimately be answered not by looking at individual objects. Instead, it might be answered by studying the statistical properties of many gravitational wave events over decades of observation. If gravastars are common, patterns should emerge in the data. Subtle signatures should reveal the presence of these exotic alternatives to black holes.